trying to draw the graph of the derivative if this is the original function. The graph of the derivative is just showing the y values here are the values of the derivative. If this is f, then this is f prime down here. So the values of the y values here are going to be the slopes here. I wouldn't necessarily go left or right. I would start with that and with that because it's easy to see the slopes are 0 there. So when you graph the derivative, this is going to be 0 and this is going to be 0. And then just look at each section in between those and maybe work from there. So from that point this way, what's true about the slope? The slope is, it's going uphill, right? The slope's positive anyways. You can estimate some things. Like if you wanted to estimate what it was right here, you know, if you had a ruler or whatever, you could see maybe it's 6 or 5 or something like that. So I don't know how you set up your scale, but maybe you made each of these 2 or something like this, and this is 4. So say you said it was 6. So it means the slope is 6 there, right? And then maybe at this point you found that it was 3 or 4 or something like that. So maybe in here somewhere. As you go along from here to there, the slope goes down. So it goes something like that. After that point, so after this point, now the slope's downhill at all these points, and it reaches kind of a minimum right in the middle there. And you might have estimated that the minimum was, what does a minimum look like it might be? Like if you drew a straight line through the middle there, 2.5 or 3 or something like that. So possibly, you know, somewhere right in here would be the minimum, depending on how you set up your scale. So it goes down to some kind of minimum and then starts to come back up again, right? It hits some kind of minimum, and then after that the slope starts to increase again. It's getting less negative, up to 0 again. So it comes back up here. It is going to be symmetric because the function looks symmetric, so this derivative graph is going to be symmetric. It hits 0 right there, and then it's more and more positive as you go here, so it's going to go up something like that. Okay? When we did this before, you noticed that we started with a function x cubed. What was its derivative? 3x squared, right? Remember I said to you that there was a pattern, or that when you start with x cubed and you do the x plus h all cubed minus x cubed and all that stuff and you expand it, the first term here is x cubed and it cancels with that x cubed. The very next term is the one that kind of survives when you put the h being 0. What power of x is the next term going to be here? When you expand that thing out, it's going to be x to the 2, right? The second term, when you expand this, the first term was x cubed, but that disappears. The next term is 3x squared h. When you divide by h, the h's disappear, and you're left with this. That's the derivative. If you go back up here, maybe it'd be better if you actually looked at the work, right? When you expanded this whole thing, this term is the one that survives the second one because all the rest of them turn into 0 here. If I started with x to the 4th, when you expanded it here, you'd have x to the 4th plus 4x to the 3rd h, right? Plus a bunch of other stuff that's all going to disappear. This is the term that ends up being the derivative. The derivative of x to the 4th is 4x to the 3rd. If this was x to the 5th, what would it be? X to the 5th, it's going to be, what's the first term in that expansion? Or first term is x to the 5th, but then the next one is going to be 5x to the 4th, h. It's going to be the one that survives. This is leading you to a rule that is known as Mr. Favreau's rule. Okay? I call it that because I challenge you to, well, you challenge Mr. Favreau to a derivative competition. He's a trained mathematician. He's a specifically trained mathematician in this one area. Okay? If you go and say to him in the hallway, if you say, what's the derivative of x to the 9th? Before you can think of the answer, he'll give it to you. It'll be quick. Even if you make it tricky and say 5x to the 9th, he'll give you the answer. That's trickier for us right now. He's the derivative king. But then if you ask him something like, what's the derivative of sine x, then he'll say, no, that's not my specialty. My specialty is number, x, number. Okay? He's very good at that. And you have to, I'm being sincere about that, because when was the last time you used calculus other than this? And he knows that. Anyways, it's not called Mr. Favreau's rule, but we can call it that in honor of his ability at that. We are going to get to that shortcut later. That isn't necessarily connected with what we're doing, but it's good to start to look for patterns like that. Did you try and do the other graph here? Well, actually, I put this question in here so you can think about what this is. If this was the depth of the water in some ditch or something like that, this is the depth of the water in one of the ditches at the side of the road or whatever, the water level is going up or down. If this is the water level, this is the rate of change of the water level. All right? Just like if you have position, its derivative is velocity, right? The rate of change of position. If this is the level of the water, what's happening between here and here? Water level's going up, it's either raining or something's happening to make the water level go up. The y values here are positive, the rate of change is positive. At this point, it stops raining, water's evaporating or draining out, the water level starts going down again. The rate of change of the water level is negative for that span. Water's leaving. This is like rate of change of water level. And then it starts raining again, and it starts to go up. The rate of change is positive, right? You have three sections in here. Derivative is positive, derivative is negative, derivative is positive. This graph's going up, then it's going down, then it's going up. The derivative is the rate of change, it's the slope. Where this graph is positive, it's going up. Where this graph is negative, the original graph's going down. As for the second thing here, I noticed some of you had started with this one and maybe you found this easier because, I don't know, for whatever reason, it's usually harder to work backwards like this. I didn't put a scale on this one because you can't really predict the scale. You don't know where it starts and ends or whatever, but this is the derivative. This is f prime. This says it has a constant slope of -1. I did tell you that it started at 0, so it's got to start there and have a slope of -1. So however you drew your slope, that's a slope of -1. Maybe I should make it less. I'll make my scale where this is -2, this is 2. And then it suddenly changes to a slope of +2. It doesn't gradually change to a slope of +2. If it gradually changed, it would go like this, right? Then you could do something like this, and then it's suddenly going up. It suddenly changes. It instantly jumps from there to there. It's got a negative rate of change, and then it suddenly has a positive rate of change. Okay? So then it's going up like that. Slope of +2. Then it gradually starts to go down to 0. At this point, the derivative is 0, so it's got to be horizontal here. Wherever it is, the thing's got to be horizontal there. It's still a positive slope here because those values are positive. So it's still got a positive slope, but it's getting lower and lower, so then it's got to be 0 there. It's got to be horizontal there, and then the slope's got to be negative on this side. So something like that. You might have had it taller or shorter. We don't know the actual y values, but something along those lines. The key things to look for are, it should be 0 here. It should have a sudden change there. It should be a slope of -1 there and +2 there. This is a tough thing to do that we will work on throughout this unit. It isn't that that's it and we're done with that and I expect you to know how to do it fully. We're going to have to draw the line here and come back to this next time. If you do want to do a bit of practice for yourself, you could try that. There's some matching questions in the book. Shows you it shows you, it's actually easier than this because it shows you the function and its derivative. It says match them up. It's quick, it's easy, there's not much writing involved.